Hi, we're going to now look at centripetal motion and look at some basics of that. Centripetal motion is a little different than the motion we've been looking at before because up to now our motion has been going, constantly in a straight line, or it's been getting faster and faster. Of course, we've had it falling or moving, but now our motion is going to produce this circle, okay? Now, when you're producing centripetal or circular motion, there's a couple things to keep in mind. One, it can translate. All right, it can translate its motional, or what we call translational motion. So the way to demonstrate that, or one little example of how we can demonstrate some translational motion. Okay, I lost my little. Here it is. Sorry. All right, one way to show that is we take this penny, for example. All right, and we start with the penny over here. So what we want to do is we want to see how far this penny moves, okay? So now we could just slide the penny, and that's the motion we've been talking about so far this year, is we take a penny and we just slide it from one point to the next. So that's our normal motion we've been talking about. The center of mass of this penny moves from one point to another. But there is another way this penny could move, right? This penny could roll, all right? So if we start with the top of the penny right here, and as we move the penny is translating its motion. So as the penny is spinning, that spinning of the penny is what actually makes it move a certain distance. Because there is friction between the pencil and the penny and the marker, the penny has moved this far. Not because it slid that far, but because it rolled that far. It has circular motion. Now, so if I want to calculate the velocity of what this penny moved, and we'll call that, it's called v sub t, or velocity tangential, or translate, the velocity that it translates. And the reason it's tangential goes a little bit further in the notes, but this rolling will translate at a tangent. The penny translates its motion at a tangent to the radius of that curve, and it's called the tangential velocity. Well, the velocity of an object is no different than any that we've done all year, and it is simply the distance over the time. So we could take out a timer, we could get us a little clock, and we could time, how fast this object is moving, or in terms of how much time it takes to move. Use our little stopwatch to determine that, okay? Now, the problem is not so much the time, but as the distance. What distance did it translate? Well, if we have this object translating, we could literally get out a ruler and measure that distance, but there's another way, and I hope you see that the distance the object translated, this purple, or whatever line you see, it's the color you see as purple, is actually the same as this right here. What is this line I'm drawing? That's right, the circumference. So when it has one rotation, it translates the circumference of the object. So the distance becomes the circumference. So the distance the object travels is the circumference, which is 2 pi r, the radius of the object, 2 pi r. Okay? Now, divided by the time it takes to do that. But there's some variation. What if it translates twice? What if it rotates twice? Okay? So now we have a single rotation. All right, a single rotation. And I hopefully see that the distance an object travels when it's rotating is equal to the circumference of that. Now, even if that object doesn't translate its motion, so let's say it doesn't translate and start over here, okay, so translational motion, maybe we say it rotates like this and it ends up somewhere over here. Because of those points, it has rolled and landed somewhere over here, okay? That's translational motion. Now, in this case, what's the distance that this has traveled? Well, each rotation is the circumference. So the tangential velocity of this object is the circumference times, all right, divided by the time still, but we need to multiply it by what? The number of rotations or the frequency. So that's italicized F. So the frequency, and the frequency is simply the number of rotations. So what is the frequent? How frequent does it rotate? So if we know the rotations, we know how much time it took to rotate, and the radius, we can find the distance, the time, and the tangential velocity. All right, so now the thing about the tangential velocity is this here. It doesn't actually have to translate it for this to be true. The object could just spin. For example, if we say, what's the rate at which this object is traveling here? Well, it's not translating its motion. The rotation that I'm creating when I thump the penny does not cause the penny to translate one circumference every time, but the outside edge of that penny is moving the circumference. Okay, so in that case, this would still be true. So it doesn't have to translate. It could just be spinning in one place. And it would still be the tangential velocity, the velocity of any point of that object would still be the distance or the circumference divided by the time times the frequency, the number of rotations. Or there is another way to write this expression. We could write this expression where the tangential velocity of an object is the circumference, distance, over capital T. Now capital T is the period, or time of one rotation. All right, so you can use either of these formulas to solve for the tangential velocity of an object. If you know how many rotations it makes and how much time it takes to make 10 rotations or 20 rotations, you could use the tangential velocity in this expression. Or you might use this expression down here, 2 pi r times the period, which is the time of one rotation. All right, so let's take a little example here. Let's say, for example, we have we just got us a car, okay, and this car is moving. Now, let's say it translates, let's fix maybe this is, I don't know, it's a school bus now or something, or a bus with a ladder on the side. Let's say that this car, okay, or this bus or whatever we got drawn here, translates 20 meters. So it moves 20 meters, okay? Now, obviously, the tire is not sliding. It's not sliding for 20 meters. That wouldn't be good. The tire is rolling for 20 meters. So, for, let's say, one rotation of the tire, you know, well, how many rotations does it have? We don't know how many rotations. We might find out how many rotations it has, okay? But let's say the radius of this tire, the radius of a tire could easily be a half a meter, excuse me, 0.5 a meter. Now, if I know the radius of the tire, and I know that 2 pi r is the circumference, I'm hoping that you see that now I know how far it rotates or translates in one rotation. Hope that's making sense to you. If I know how far it translates in one rotation, then I can tell myself how many times it rotates to make 20 meters, which then is going to translate into the tangential velocity of the tire. Okay? Now, the tangential velocity of the tire does not necessarily represent the tangential velocity of the bus, because we're talking about the velocity of this point on the tire at that, which could be different than the tangential velocity there. All right? Now, there's one other thing I want to tell you about the tangential velocity. If we have an object that's just rotating, it's rotating and spinning, okay, and we say that it has a tangential velocity of 1 meter per second. If that object were to fly off at a tangent, it would now have a velocity of 1 meter per second. So if the tire on this bus is rotating at a tangential velocity of 20 meters per second, and it were to break off, then it's going to roll down the highway 20 meters per second. Okay? So at this point, we'll have some questions for you to solve on centripetal motion, the velocity of an object, and you're going to use these two formulas here to solve them. So there'll be some of those problems available. Okay? All right, next, guys. If it has a velocity and it's rotating in a circle, then it probably has a centripetal acceleration. So we won't go through all the derivative of this, but I'm going to give a brief discussion, and then we'll show you the formula for centripetal acceleration, okay? So basically, if we have an object that's rotating, it has a certain radius here. And so what we can do is we can draw, even though we label this capital R, it's still lowercase r, the radius. So all of these are equal. So if this is a radius of 1, for example, and this is 1, then we're saying that this chord, capital R, is also equal to 1. All right, so if we go right here and we say this object is going to fly off at a tangent to that point, v sub 1 is there. All right, what's the velocity at this point? I'm actually going to redraw it. I kind of misdrew that vector a little bit because of the way my paper was sitting. It's going to fly off over here somewhere because it's going to fly at a tangent to point 2. Okay? So what happens is, now I have two vectors. So I can come over here and I can say vector tangent 2, and I can add that to velocity vector tangent 1. Now these aren't added correctly because they're not connected head to tail. So I would slide this vector over here. And now what I get is I get the resulting vector, which is the change in v. So this vector 2 plus vector 1 is how much the velocity has changed. Now what's happening is the length of that vector has not changed. The tangential velocity has not changed. The direction is what has changed. Okay? So if it's going 20 meters per second here, well, it's still going 20 meters per second here. But here it's going 20 meters per second at, say, 95 degrees. Here it's going 20 meters per second at 180 degrees. So it's, when you're calculating this change in velocity, you're not calculating the rate at which it's spinning faster. You're calculating the rate at which the direction is changing. Now, it still looks like an acceleration. It still would be 20 meters per second squared. The unit would be just like any other acceleration unit, a meter per second squared, okay? But it's not the rate at which it's spinning faster, it's the rate at which the direction is changing. So if we go back to these little diagrams here, basically in the end, we have R1, R2, and we have similar triangles, and we can derive an equation that says the centripetal acceleration, which we label as A sub c, centripetal acceleration, A sub c, is v squared over r. And that comes from similar triangles and the algebra manipulation between those expressions that I'm kind of drawing there. A little bit more to it than that, but that's the basics. So the centripetal acceleration is v squared over r. The velocity of that object is going to be the circumference over the time times the number of rotations, or 2 pi r over capital T, the time of one rotation. So you would solve for this and simply plug it in there. All right. Now, one thing to think about now is if it has motion, it'll have a velocity. If it has a velocity, it has an acceleration. We want you to solve a couple of those problems. We'll put some of those up. To now, it would have a centripetal force. So if you have an acceleration, you have a force, because things only accelerate when the net force is non-zero. So we want to answer these questions. What direction is the centripetal force? Well, the short answer is towards the center. All right, towards the center of the circle. The equation would be force, centripetal, F sub c, or centripetal force, is the mass of the object times the centripetal acceleration. Now, this number could or could not be, may or may not be equal to the acceleration of the object, the linear acceleration, okay? two different numbers. The linear acceleration could be how fast it's getting linear down the line, how much faster. But at the same time as it's getting faster, the tire is rotating more and more and more. The direction is changing. So it gets a little tricky there, but that's the idea, centripetal acceleration. So we can write this expression as force centripetal is the mass v squared over r, because now we've substituted our centripetal acceleration equation into this, okay? So centripetal acceleration creates a force. That force is always towards the center of an object, and the formula is simply mass times v squared over r. At this point, we want to talk about this path of inertia, because if you've ever spun an object, if an object is rotating, and if you have an object on a string and it's rotating, and you let go of it, it doesn't fly towards the center. It flies off in a straight line, which is Newton's first law. So Newton's first law says it travels off in a straight line. This straight line is called the path of inertia. All right, so down here, we have an object that's attached to a string, so we have some weight. And this object wants to travel in a straight line. It wants to have its path of inertia. According to Newton's first law, it wants to travel in a straight line. But what we're going to do is we're going to attack, because this is attached to a string, this string pulls it towards the center. This string represents the centripetal force. And what happens is you see the resulting motion of these. So if this is our center point, so here's another centripetal force here towards the center. So what you see is you see this path, the resulting path. So what does it do at that point? At that point, it wants to fly off its path of inertia in a straight line. But don't forget, there's this centripetal force that's pulling it back towards the center, okay? Pulling it back towards the center. And what you see is the result of those two. So at that point, what's it want to do? It wants to travel off in a straight line. But there's a force pulling it back towards the center. And you see the result. Okay, so I'm going to quickly finish this up. Now it wants to travel off in a straight line, but it's trying to be pulled back to the center of the circle. And you see the result. And that pattern completes until it goes all the way around. So this idea of path of inertia is an object wants to follow its path of inertia, a straight line. But because there's a force pulling it towards the center, the result of those two vectors produces an arc. And that arc is constantly repeated until the object travels in a circle. So the centripetal force of an object is always towards the center. But if you're rotating, you get thrown out. So there's a force towards the center, and there's this force out of the center. It's our action-reaction force, right? Newton's third law. If there's a force pulling you towards the center, there's that force trying to travel out. But you're actually not trying to travel out. You're trying to fly off in a straight line. You're trying to go your normal force. So if I cut this string, if I remove the centripetal force, the object does not fly out. It flies the path of inertia, a straight line tangent to its circle. So the centripetal force of an object is simply calculated by FMAC, or mass times v squared over r. The centripetal force is always towards the center of a circle, even though if you feel that force pushing you out, okay? So if we take this, let's take this little pin and move the cap. If I spin that cap quickly, the cap doesn't, the cap doesn't get pulled closer to the pin. If I spin it up here, the cap flies off somewhere over here. Why does the cap fly out? There's no force actually going out. That's the path of inertia. The cap didn't fly out. No. The cap flew in a straight line, its path of inertia. Because there wasn't enough friction between the cap and the pin, to keep the cap pulling in. So examples of centripetal force, okay? Examples. Tension in a string. So when you rotate something with a string, that string is pulling on it. Friction on car tires. Okay, friction on car tires. All of those things are examples of centripetal forces. All right, so this time we're going to put some equations and some examples for you to solve for centripetal force. You should be able to manipulate these expressions and solve for mass, v squared, and r. All right, guys. Thank you.